start here. So I'm going to start with the first section of the book. And so ideally, if you don't have it ready this time, just have it ready for next time. Um, Ideally, you'll have these either printed out or on some sort of tablet. Um, and usually, if you just copy, more or less copy and make the marks I make, you'll get full credit. All right, so let's talk about real numbers. So real numbers are any number you can think of. So if you can think of a number, it's a real number. Um, the only thing above this is complex numbers. Are there other systems beyond this? Yeah, there are, but you don't need to worry about them. So let's start with the most basic numbers. These are the natural numbers. This is 1, 2, 3, and 4. This also includes things that look kind of strange. So the square root of 4 is 2, so that technically is a natural number. 2.0 still is 2, so that's a natural number. This is a fraction, which is still 2. So this is a natural number. So natural numbers are the numbers including 1, 2, 3, and 4. And so basically this kind of goes the way um, they were discovered. So once upon a time, humans did stuff without numbers, right? So there was a shepherd, and so a shepherd, in order to deal with life without numbers, for how do you know if he had all his sheep when he came back home that night, right? Or all this other stuff. And so they let him out. And what ancient man used to do is they had a pile of stones, and they had one stone for every sheep, right? Because they didn't know how to count. They legit number two wasn't a thing to them, right? And so as the sheep left, they put one stone into another pile, right? And says, okay, that sheep's out. When it came back in, they take that stone, put it back in. Then someone figured out how to count 1, 2, 3, 4, right? Later on, zero was added. This is actually was an invention for math, right? And we can have a placeholder for nothing, right? So if you have your natural numbers with the zero, that's whole numbers. And then we had uh, it's a joke, but economics was invented. And then you could have negative numbers. You could owe people money. Um, so you can own negative things. So 1, 2, 3, and 4. Okay. And then we had fractions. And so rational numbers is anything that can be written as a fraction. So 1/7, that's a fraction. Uh, Negative 14/3, that's a fraction. And so these can be both positive and negative. Notice here that real number or rational number, anything that's a natural number, sorry, it's also a whole number. Anything that's a whole number is also an integer. Anything that's an integer is also a rational number. So that's why these boxes are kind of nested the way they are. Um, if so, all these are rational numbers. Negative 3.1, 154545454. This little bar, if you guys forgot, means repeat those digits. So 5 and 4, not the 1. So 5 and 4 will repeat forever. If you have any sort of repeating decimal like this, you can write it as a fraction. I could teach you that, but we're going to skip that. It's not necessary. Um, and then over here we have the irrational numbers. So irrational numbers are things um, the decimal form does not terminate, right? So this doesn't terminate. So all of these, pi doesn't terminate, e doesn't terminate. We'll deal more with e later. Pi is defined to be the circumference of a circle. That's how it is defined. Um, and you can watch these fun YouTube videos. They print out like a mile worth of pi digits and all this other stuff. Um, Square root of 2 is not a rational number, and it was proved back in the time of the Greeks. And the Greek who proved that this wasn't a rational number got kicked out of his little Greek society um, because they said we liked everything being nice and beautiful, and he proved that everything's sometimes it's not. So they got mad and kicked him out. Um, so there's a couple notes. Rational do not repeat or terminate. So anytime it repeated, you could write it as a fraction. And there are a lot more irrational numbers than rational numbers. In fact, there's a magnitude of infinity more of irrational numbers than rational numbers. Um, and so a real number is either rational or irrational. Um, but the amount of these is that. So if I took a dartboard and randomly had all the numbers on it, and I threw a dart at it, the chance of me hitting a rational number is zero. It's not close to zero, it is zero, right? That's how many more rational numbers there are. Oh, you guys are engineers. I'm going to teach you something real fun real quick. So, but real quick, between any two rational numbers, so here we have a rational number, so 3, 4, 5, and 1, 2, 3, 4, 7. So these are both rational since they terminate. Between any two rational numbers, there's an irrational number. So I could have 1.34 426 dot, 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 right? So have this be even, I don't need it. So between every two rational numbers, there's an irrational number. You can easily just think of something that just doesn't work. And between every two irrational numbers, 1.34, let me make this smaller. Hold on. There we go. And I said 3, 4, but I did not write 3, 4, 2, 8, dot, 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 dot. Between every two rational numbers, at some point, one of the digits will differ. If not, they were the same irrational number. The second they differ, you can just truncate the larger one, and then you have a rational number between two rational numbers. But the fact that there's still infinitely more irrational numbers than there are rational numbers holds. And so it's kind of weird things like between every two irrational numbers, I can write a rational number, but there's just so much more less of it. You think it'd be a 50-50 chance to pick a number. It'd be rational or irrational, but it's not. Math gets weird when you get really deep into it. That's just a side note. You don't really know that, but it's just a fun side note. Here are the common symbols. They look like this. So natural numbers have, when you draw it, you just draw, usually I just do an N and you just do a double bar right here. This is the fancy math font they use. This same for Z. You just put a double bar right here. For the Q, you just put a bar right here. And for the reals, you just put a double bar on it. So these are how you denote the set of numbers. This is helpful later when you do proofs where you have to do A exist as a real number. And so you say this is a real number. That's how you would write it. Okay. All right. So let's go on to the next section. Real quick, when filling out the notes, you do not need to worry about, a lot of times I'll circle stuff or put arrows and stuff. You don't have to make those marks. Okay. In fact, you don't even really have to make, oops, where'd it go? You don't really have to make these marks as well. Let's go back to here. Oops. Make this. All right. So let's identify some of these. All right. So what is A? What is A? I'll have some of you write in chat. What is A? That number is what? I'll ask you every now and then. I'll ask you guys to write 1 or 2 things in chat, just so I make sure you're alive, or at least somebody is. Yeah, this is rational. Yeah, this is a rational number. And in fact, identify which categories. For this case, for this sort of thing, it's also a real number. All of these will be real numbers, so I'll just go ahead and fill that in everywhere. Real, real, real. Okay. Here, for B, the square root of 49. This is equal, so square root of 49 is equal to 7. So this is not only, this is a real number, but it's also a rational number. It's also an integer. See if I can spell all these. Hi. It's also a whole number. And it's also a natural number. Okay. And so in this case, what category does this belong to? I can say 7 is a real number. That's accurate. I can say it's a rational number. That's also accurate. I can say it's an integer, a whole number, or a natural number. All these are accurate. Same thing for here. So this is also a rational, and it's also an integer. And the reason I'm going over this is I want you to understand that numbers can be part of more than one category. Okay. And so it's good to know. It's kind of like I'm a human, right? That's one category, but also I'm American. That's another category, right? I'm also, um, 36-year-old, right? That is a category, right? So numbers, like things, can go to more categories. And so sometimes in math, we get in very binary sense. It's either this or that. Um, but some things are not that way. Here, notice this is repeating like this. So it goes on and on and on. So if you saw this right here, you'd think it'd be irrational. And probably since I haven't identified what that is, it'd be a valid assumption. But here, this is rational. And then this is pi, which is irrational. Okay. Um, let me open up something really quick. Digits of So here's a fun little website. So here's the first couple of digits of pi. So the first 10 digits, yeah, that's nice. Let's look at this. Notice how pi just becomes a mess, right? I don't know if you guys ever looked at this. Just becomes a mess of who knows what, of random digits, right? And this goes on and on and on and on and on. Oh, I hit the bottom of the page. So yeah, so pi is really, oh no, so it goes on and on and on and on. It's just a mess of randomness for all we can tell, right? So that's what an irrational number looks like. That's really what they look like. And this isn't all of it. So it's nice to kind of see that once if you haven't done it. All right. So when you write out the notes, you need to write out these, but here are stuff in the boxes we want. So properties of real numbers. Commutative property. The commutative property for addition basically means I can swap the order of my addition. For multiplication, I can swap the order of my multiplication. This is true for all real numbers. You'll get into other systems where in math that may not be true. We'll actually get to one. We'll get to matrices before the end of this term. And the commutative property of adding it is true, but the multiplication property is not. The associative property, this is where I can add them in any order or multiply them in any order. Um, this is actually really, really hard to break, even in really weird number systems for math. So this is hard to break. Please notice that your, I don't know, what is it? Is it pen? Um, I don't remember what do you guys use to remember order of operations now? PEMDAS. Okay. Uh, in middle school, I used to read it on the wall. I could only remember. Yeah. All right. So this goes first. This goes second. These two actually go together, and these two actually happen together. Okay. Um. So you actually put them together. So it's a little bit misleading. Um. So just do remember this. There's actually competitions where people remember how many digits of pi, and I'm just I'm just not there. And this is your distributive property. That means if you have something outside, you can put it in. And this is the right distributive property. This is the left distributive property. Since we're in a commutative ring. Technically, that's what the operation we're using here. Um, that doesn't matter. These are basically the same. These are examples. All right, so let's do the next page. Nope. I need to make 2 layers first. Layer, layer. All right, properties of negative numbers. All right, so here's properties of negative numbers. The product of two negative numbers is a positive number. Product of a positive number and negative number is negative, and a product of zero of any number is zero. So there's no such thing as a negative zero. So I've seen that, just putting it out there. Um, Another thing here, if I have a negative, I can distribute the negative. And what I'm really doing is I'm saying this is a -1 and then distributing a -1 into both of this. Same thing here. If I have a negative and a negative, I can swap the signs. So when I'm simplifying the following of these, let's see if I can do basic math today. So here, a negative times a negative will be a positive 42. Here I have a 0 and a negative. Well, this is 0. It's not -0, just 0. Here I have a negative, a negative, a negative, and a positive. And so what you really end up doing here, this is 4 times 3, which is 12, times 2, which is 24, times 2 more is 48. So what I tend to do is I tend to multiply all the numbers and then figure out if it's positive or negative. And if it's an even number of negative signs, it's positive, and if it's an odd number of negative signs, it's negative. And so here I have 1, 2, 3, that's odd, so make it negative. Okay, so if you have like 5 negative signs, that's negative. If you have 7 negative signs, that's negative. If you have 2 negative signs, it's positive. If you have 4 negative signs, it's positive. You have 0, which is an even number, that's also positive. Here, when we do this, when we distribute this -1, this is -3 plus 5. And the reason I have this as its own separate thing is that, you know what most people get wrong in calculus? It's not the calculus, it's stuff like this. I will be dead honest with you guys. They're so focused about doing this really advanced derivative, they go and they forget how to do this stuff. Just what happens. Don't feel bad if it happens to you. I did the same thing. Okay? So just be very clear on why negatives move and do as they're supposed to do. A quotient of 0 and any non-zero number is 0. So 0 over b is always 0. So if I have 0 parts, so if I have 0 sevenths, I have no parts of the 7th part of a pi, right? A quotient of a 0 number and any non-zero number and a 0 number is, you know what, for this class, get rid of this non-zero. Of any real number, because 0 over 0 is undefined for you guys as well. It just is, right? So I don't need the non-zero part. Your book may read it that way. Don't ignore it, right? So if any real number in a 0 is undefined. So anything over this is undefined. So here, -15 over 5 is how I'd write it as a fraction. So this just becomes -3. Here, if I have 0 over 2, that's the same thing as -0 over -2. This is 0. And -5 over this. For some reason, I wrote the answer, not positive. But why I did that? But I did. I wrote all these notes for you guys. So that's undefined. So just 0 over a number, 0, anything else over anything over 0, undefined. Okay. Now you will deal with that later and define it later, but we won't do that yet. All right, here's everyone's favorite thing, properties of fractions. I find this tends to be awful. So multiplying fractions, you just multiply across. So a plus a times c and b times d. As long as if a and b are real numbers, you can do this. So that's what I did here. Notice that's kind of what I did here is I turned, hold on. is I turn this division into a fraction, right? Took the division, made it a fraction. So this division turned into a fraction, and then I just simplify the fraction. It's just how I do math. You don't have to do it that way, but as long as your b is not a 0, you can do it this way. If the b is 0, this is just undefined, so you just don't even worry about it. We call the expression 1 over b the multiplicative inverse of b or the reciprocal of b. So you'll see these used interchangeably. You guys are probably way more used to the word reciprocal over multiplicative inverse. It's probably what you're used to. What multiplicative inverse means is if I take b, what do I multiply it by to get back to the 1 or the identity unit? You'll get to that in deeper stuff. If you're dividing fractions, you just flip the second fraction. So a over b becomes and multiply, so you just flip the multiply. Subtracting, if it has the same denominator, you only have to deal with what's on for the numerator. And if they have different denominators, you make it so they have the same one. You can multiply b times d and then do cross multiplication. That's fine. Common factors, if they have both common factors, you can clear it out. Cancellation property exists for a lot of things, but not for everything once you get really deep into math. If A equals B, this is cross multiply, right? Where you just multiply this times this and this. There is an error here. Woohoo! This should be a B, guys. Sorry about that. Please make that correction. B times C. All right, so here we're going to perform the indicated operations. All right, so I'm going to do a couple of them, and I'll have you guys write at least one in chat. So here, we're going to perform this indicated operation. What I probably want to do is write this as a fraction. So if something's not a fraction, you can always write it as a fraction by putting it over 1. And then here we can just multiply across. I'll have minus 6 over 3, which simplifies, of course, to negative 2. Okay. Here, I guess I should do it in order. Here we can do cancellation. So I can cancel this so that I have 3 here and a 3 here. You can go ahead and cancel before you do your operation. That's perfectly okay. And by doing so, I have negative 2 over 4, which is equal to minus a half. Notice if you put the negative 1 here over 2, or this is equal to 1, negative 1 over 2, which is equal to 1 over negative 2. All of these are equivalent. These technically are saying different things. This is negative 1 divided by 2. This is the negation of the fraction, a half. And this is 1 divided by negative 2. Technically, these are different, but for real numbers, these are all the same. So where you put the negative sign doesn't matter. This is standardly where you put it. When I'm filling out notes, I almost always put it on top just because of my handwriting, I guess. All right. So for this one, if I have negative 1 divided by this, I'm going to write this as negative 1 over 1. I'm going to multiply, and then I'm going to flip this fraction. And so here I'm going to put negative 4 over 3. And for this, I like to stuff the negative either top or bottom. And the reason I'd like to do that is that when I do multiplication, it's clear what's going on, because my bottom or my top will both be positive and or negative. And so when I do this, negative 1 times negative 4 is a positive 4, and 1 times 3 is a 3, and so we're good. Here we're going to add 2 fractions of the same, let me go here. So here we're going to add 2 fractions of the same, we're dividing. So here I have the negative both times. I'm going to put both my negatives up top. And the reason I wrote this problem so I could show you that. And then I'm going to multiply and flip this. And where am I going to put my negative? Up top. I just standardly always put it up top. That way I'm always doing the same thing and it's always easier for me to handle. Try to make math easier for you. Try to do stuff conventionally the same way. If it doesn't matter, it's still nice to do it conventionally the same way so you know what you're doing at least. Okay, so once we do this, before I even do this part, so once I've flip and multiply here, the 4 and the 3 don't cancel, but here I can cancel out a 5 and make my life easier. And so up top I'll have a 1 times -1 times -3, so that'll be a 3, and I'll have 4 times 2, so this will be an 8. So this will be 3 8s. Okay, so what I'm trying to do here is not only just do a couple fractions to show you, but kind of explain my thought process. And yours might be completely different, and that's fine. But I want to explain my thought process as I do these. That way you can kind of see how I think through it step by step. Here I'm adding stuff that are the same denominator, but still here I once again always put the negative up top. And that way I kind of know what I'm doing. So here the 4 remains the same, so I'm just using this one, and so I'm just adding what's up. So -3 plus 5 is is 2 fourths, right? So 2 divided by 1, and then here we simplify. So the question is, do you have to simplify fractions? That always is a question for me. Does everyone have? The answer is no. In this class, as long as you get to this part, I'm okay. However, it is a good practice to always do this. So I won't mark it wrong if you don't simplify, but please do simplify. It's a good practice to do. The last one here is this. And so according to what the book has asked us to do, is we're just going to multiply across. And so I'll multiply this by 4, this by 10, and proceed to do what I need to do. But notice here, I can go to 20. Both of those go to 20 real easily. And so let me explain my thought process. And I want to do this and leave a lot of room. So I'm going to leave some room. So I'm going to leave room here. So I want both of these can get to 20 quite easily. And so I can have a simpler number than 40. 40 is where the book would send you. Just multiply across, it works. Yeah, that's true, but the least common multiple right here would be 20, right? So how do I get there? I need to multiply 4 times 5. But I'm also going to multiply by 5. Notice that 5 over 5 is equal to 1. You can always multiply by 1. And so we're going to do this a lot in this class, but sometimes the ones are going to look weird, right? They're going to look like the square root of 3 plus 1 over the square root of 3 plus 1. It may seem really weird to multiply by that, but this actually allows us to simplify things. So we're going to start with 5 over 5. So this is multiplying by 1. So I've actually changed nothing here. And here, in order to get to 20, I need to multiply by 2 over 2. So I'm going to do this multiplication first. And so this gives me 5 fourths minus 18. Oops, I said 5 fourths, but that's not what I got, is it? Hi. What? Oh my goodness, what is going on? Why is my eraser busted? There we go. It's 5/20ths over 18/20ths. And then once we do that, we can get 5 minus 18 would be minus 13/20ths. Okay. So multiply by these ones. If you skip from this point to this point, that's fine. I usually do this in my head, go from here to here and from here to here. But just for the sake of writing notes and explaining stuff in class, I'm going to be pedantic. And what pedantic means is overly detailed. And I find, well, that might bore some students. And if you're bored a little bit, I'm sorry. But I'm not going to, sometimes you just look up and it's like, I have no clue how that happened, and no one raises their hand. So I'm going to err on the side of being a little bit explanatory. Okay. All right, so let's just do the very last thing. So we have a collection of objects. Intersection of two sets of what's common between them, and the unions between this. For some reason, I don't think I wrote any problems for that. So yeah, so here, let me just do it real quick. So if I have A and B intersect B is the things that are common between them. So 1 is not between them, 3 is in both, 5 is in both. So we'd have bracket, I can make it look like a bracket, 3 and 5, because that's in both of them. And then if I did A union B, it's what, so it's everything. So I'd have a 1, a 3, a 5, a 6 from this. And then 3 and 5 are already in there, so all I have to do is add the 7. Okay. This doesn't come up too much in. Do we do sets in calculus? No, we don't really do too much of this. This, however, comes up all the time in calculus. So different ways of representing inequalities. We'll work with equations later. So just to be clear what I want, so here's the inequality written as an inequality. This is in interval notation. This is in set builder notation, and here's the graph. Let me explain set builder notation. So this right here, so this part here and this part here means the set of, so that means the set of. I'll go ahead and use different colors real quick. Here, this is the element. And so here, our elements are 1, 2, 3, 4, 5. Here we're going to say the element X. This line here, I'm going to do that in a different color. I'm doing it in dark brown. This line here means such that. And then I guess in orange, we're going to have X less than 5. And this right here is our condition. So this means the set of all X such that X is greater than 5. Okay. Go back to my blue now. So here we have greater than or equal to. So here we're going to use a bracket of 5 and the infinity symbol. And then we're going to have set building notation is this. It's going to be X less than or equal to 5. And then here we're going to go from 5. And we're going to, instead of this, we're going to put a bracket in here. I'll go ahead and draw the arrow that way. Here, for this, we're going to have, oops, infinity always has the parentheses. So this means the bracket means including, the parentheses means not including that number. So here we're going to have from negative infinity, which we never include, up to 5, not including. So this means not including it. Set builder notation, X less than 5. And here I'm going to show you the other notation. So here I can have an open circle and a line. And here if we have the, oops, infinity to 5. And then we'll have X greater than or less than or equal to 5. We can have a closed circle. So here's the two options. I'll just show you one. You can pick whatever one you choose to. You can have the parenthesis bracket option or the open circle, closed circle. I think you guys are more often taught this version, but I don't know. You might have a different experiment. They now teach, oh, what's the new